Light is our greatest key to seeing the universe, to observing it. But it's unlike anything we've ever seen. By the 17th century, scientists were well aware that light traveled predominantly in straight lines and that it could reflect and refract as it traveled. And around the same time, Sir Isaac Newton conducted an experiment through which he showed that white light can be split into the rainbow using a prism, and that rainbow could be turned back into white light using a mirror. To explain such behaviors of light, two guys created their own models, Newton himself and Christian Huygens. According to Newton, light was made up of particles that he called corpuscles, and according to Huygens, light was a wave. These two theories did have their own pros and cons, but the corpuscle theory was far more popular, as Newton and his laws of motion reigned supreme at the time. Seriously, in his particle model, Newton said that light travels in straight lines because of his first law of motion, because there are no forces acting upon the light particles, the corpuscles. Both theories were basically on even ground, up until the 19th century. In 1801, a chap named Thomas Young conducted the now famous double slit experiment. Young set up a source of light beams and passed the light through two tiny slits. Behind was this flat wall thingy, kind of a detector. This is how the experiment looks from above. If light was a beam of particles, you'd expect the pattern on the detector to look like this. But that is not what Young saw. He saw this. This pattern is called the diffraction pattern. Sound familiar? Indeed, light is a wave. And according to Huygens' wave model, as the light passes through the slits, it is diffracted. And subsequently, those diffracted beams then interact with one another, both constructively and destructively, before hitting the detector. On the detector, the bands of light represent the regions of constructive interference, whereas the dark bands represent the regions of destructive interference. Decades later, a Scottish genius named James Clerk Maxwell realized something as he was studying electromagnetism. A charge will generate an electric field that surrounds it, while a current-carrying wire will generate a circular magnetic field. Maxwell postulated that any changing electric field will induce a magnetic field, and that any changing magnetic field will induce an electric field. And these electric and magnetic fields could propagate through space in the form of a wave, an electromagnetic wave. This wave would travel at 299,792,458 meters per second. Yes, light. Light is just a wave of electric and magnetic fields oscillating perpendicular to one another. This is a mathematical representation of what the wave looks like. By now, physicists were getting really confident in the wave theory. Light was a transverse wave, just like the wave on a rope. But this wave here on the rope has a medium that it's traveling through, the rope. So does light also have a medium that it's traveling through? That was a burning question of the 1880s, and physicists assumed that there indeed was a medium through which light traveled, called the luminiferous ether. This ether was said to permeate the entire universe, and it behaved kind of like the Earth's atmosphere. When you are moving on Earth, you sort of generate this kind of wind as you bump into the air particles. Similarly, since we, on Earth, are orbiting the Sun, and the Sun is orbiting the center of the Milky Way, and the Milky Way is flying around the universe, we humans are moving relative to the ether. And because of that, we would be experiencing ether winds. And because of this wind, light would travel at different speeds in different directions. That was the argument. Think about it like this. On a windy day, when you yell against the direction of the wind, your voice doesn't go very far at all. But when you yell with the wind, your voice goes really far. Same with light and the ether. If light were moving with the ether winds, it would travel faster than as compared to if it were moving against the ether wind. Now, the ether itself was said to be very difficult to detect. It was invisible and didn't interact with much. And so, two guys set out to detect it. Albert Michelson and Edward Morley, in what would become known as the TheelsonMorley Experiment. They set up a source and directed a light beam onto a half-silvered mirror. This mirror would let half of the light pass through and reflect the other half. Basically, the original light beam would be split into two. Those two new light beams are then each bounced off of two other half-silvered mirrors and subsequently returned to the original mirror, from where they converge and hit a detector. This whole setup is called an interferometer. If there was an ether and some ether wind caused due to the motion of the Earth relative to the ether, each split beam would travel at different rates, would have a different speed, and hit the detector at different times, causing an interference pattern that shows the difference in their speeds. But that's not what Michelson and Morley saw. They observed an interference pattern which demonstrated that both light beams traveled at the same rate. They didn't change their speed. The ether wind wasn't affecting their travel. There was no ether wind. There was no luminiferous ether. Light, despite being a wave, does not need a medium to travel in. It just travels through a vacuum. Pure emptiness. And it was Albert Einstein who realized that the speed of light does not change with the reference frame in which it is viewed. So red, blue, green, violet, orange, all these colors of light, they are fast, lazy, cool, but weird. They all combine to form white light. In sound waves, the frequency determines the pitch. In EM waves, the frequency determines the color. Red color light has a large wavelength, and so a low frequency. On the other end, violet light has a smaller wavelength and a large frequency. But visible light isn't the only type of electromagnetic wave. You see, there are many different types of electromagnetic waves. There is a whole spectrum of electromagnetic waves, the electromagnetic spectrum. Beyond violet, you have waves with even greater frequencies, UV, X-ray, and gamma. And beyond red, you have waves with even smaller frequencies and larger wavelengths, infrared, microwaves, and radio. None of these have any sort of color because we cannot see them, but we can observe their effects and manipulate them for different purposes. Fun fact, did you know that Hulk was formed because Dr. Bruce Banner was overexposed to gamma rays? Indeed, physics controls the Marvel Cinematic Universe. Not really, but never mind. Light is a bundle, a wave of changing electric and magnetic fields. This model explains why light slows down in a medium. Remember that everything is made up of atoms, and atoms have a nucleus in their center and electrons orbiting on the outside. These electrons have a negative electric charge. When light enters this bond, it interacts with the electrons in the bond's atoms. As a result, a second oscillating electric field is induced. The electric field of the light then combines with the new oscillating electric field. This is superposition. The combined wave of light and the oscillating electric field now is what travels through the rest of the pond, not the light by itself. And this combined wave travels slower than the speed of light in a vacuum. It travels slower than 299,792,458 meters per second. So, light slows down in a medium because it interacts with the electrons in the atoms of the medium to produce a new oscillating electric field with which it then combines to form a new wave that travels slower than the speed of light. Whew, that was a mouthful. Alright, so the wave model explains a lot about light. And indeed, the answer to the question, what is light, is that light is a wave. Case closed. Or is it? That the speed of light is always constant in a vacuum, no matter your reference frame, is not the only thing that Einstein had to say about light. He also said that, well, it's kind of a particle as well. I know it seems ridiculous after everything we've been through. So let's just give ourselves some time for denial. And then we shall shine light on the truth about this issue. Hi, thank you for watching this video. If you feel certain explanations weren't understandable or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I have also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.